Bam! Mr. Tarrou, on this dark and stormy day, we are going to have an algebra lesson involving characteristics of graphs, just in case you happen to hear some thunder outside. In this lesson, we are going to be, through the use of these 10 example graphs we already have up on the chalkboard, we'll be introduced to the definition of a relation and a function, identifying whether a graph is discrete or continuous. We're going to be looking at identifying, just visually in a graph, vertical and horizontal symmetry, whether a curve is smooth, identifying with an example where a graph is increasing or decreasing. We've touched on that already a little bit in a previous algebra lesson. We're also going to be looking at 3 of these graphs, actually maybe 3 different examples of graphs, and identifying from the graph again, just the graph, what is the domain and range? What is the domain and range? The kind of the x and y values that are included in the graph. Now this is an algebra lesson, so this is going to be an overview of a lot of these definitions, but all these definitions have more applications the farther through mathematics that you go. So through the lesson, if you want a more in-depth understanding of the difference between a relation and a function, I'll include a link in the lesson, probably above my head, that you can click on and go to that lesson. It's, well, maybe finish this lesson first, that you can go to deepen that understanding. And I'm also going to include links in the description in case you're maybe using a mobile device and you don't have Flash. Same thing with whether a function is continuous. There's fancy ways of proving if a function is continuous at a point in calculus, using an idea called limits. Same thing of a smooth curve. In an algebra class, we're just going to kind of look at visually at how the graph looks, but there's more in-depth ways of proving that, proving whether a function again is continuous or smooth at a point using some calculus techniques. And so if you need more understanding than I'm giving you in this lesson, well, then you'll know where to go. And if you are just an algebra and you're kind of like going, well, how is this going to get used later, at least mathematically, you can go to those lessons and get, a more in-depth understanding. But for right now, what I would like you to do is, I'm going to step off. I would like you to look at these 10 graphs and group them just, by visual characteristic. How do they all look similar? And maybe create, 6, 7, 8, 9 groups of like type graphs by some visual characteristic. And then I've come up with my own groupings already. Maybe I'll do more groupings than you, maybe less. But how I looked at these, and I'm going to use these groupings to, introduce the definitions that I just said we were going to go over in this lesson. So, pause the lesson, make those groups. I'll be back in just a minute. For my first grouping that I came up with, we have graphs A, C, E, F, G, and H. And sorry for covering up J. I guess I put it in a bad spot. But the reason why I have these all grouped together is because when I look at them, well, if I use this my chalkboard compass as a straight line, anywhere that I place a straight line, my straight line is only intersecting these graphs at one point. Like, whereas D, the reason why that's different, if I place a vertical line here, I am crossing the graph twice. Okay, now a vertical line, depending on where you are in your algebra studies, the equation of a vertical line is x equals a number. If I say, well, let's see here. Actually, the points that I covered up, those blue dots are in a vertical line. This is point 0, 1. This is, actually, excuse me, I just misspoke. 0, 1 is right there. When you plot a point, the first number, the x, tells you how to move left and right, and the second number, the y, tells you how to move up and down. So 0, 1 means from the origin, don't move left and right at all, 0, and then 1, move up 1. So, excuse me, this first point is 1, 0. 1, move over 1, 0, don't move up and down at all. This point, this coordinate of this point is 1, 1. The coordinate of this point is 1, 2. The coordinate of this point is 1, 3. The coordinate of that point is 1, negative 1. That point is 1, negative 2. Every time I point to one of these blue dots, I'm saying the same x coordinate, 1. Okay, so when you look at a vertical line, the equation of a vertical line is x equals a number, because every point on that vertical line is going to have the same x coordinate. So as I hold up my compass in an up and down fashion, or as a vertical line, I'm really identifying an x-coordinate. And so for each of these values of x, for each of these values of x, for each of these values of x, that vertical line is only crossing the graph once. Well, that means that for every individual value of x, there's only one y. That's identifying, whether you've heard this definition or not, that these graphs are all functions. A function is a relation. Now, this is a bit of a problem because, at least in this video, I have not defined yet what a relation is. So I'm using a vocabulary word that you don't know yet, so I'll make sure I clear that up next. A function is a relation such that for each element of the domain, there is exactly one element, that's basically number, in the range. Okay, well, this idea of element is just really just a number for our purposes, and, well, really for any graphing purpose. And it's talking about domain and range. So there's a couple of words in this definition of a function that you may or may not know. Now, if you're watching my algebra lessons in order, we've already defined what domain and range is. The domain is an input value into an equation, or at least when you're talking about graphs on the Cartesian plane, an x, y axis plane, then the domain are simply all of the x values that are included in the graph, and range, if you have an equation, is the output value. It's the answer that you get from your equation. Well, graphically, that means, at least on these Cartesian planes, that the range is going to be the y value. So domain is x, range is y. So for every value of x, there is only one y. And again, that vertical line that I'm holding up with my compass is representing an x value. And if it's only crossing the graph once, then for that x, there is only one y. And indeed, with a function, every single x in the domain, every single x value can only be paired up with only one y. A relation doesn't have that limitation where every x can only match up with only one y. So for a relation, if an x can be paired up with more than one y, which of these graphs would be a relation? And that'll be our second grouping that we discuss, and I'll have that definition written on the board. Graphs of B, D, and graph J that I covered up, those are all relations. Again, if I hold up a vertical line representing a value of x, in this particular case, that x value is connected with or related to two different y values. Thus, it is a relation. Now, a relation is a set of ordered pairs. And by the way, an x value can be connected with, or a single x value could have 10 different y values that it's related with if the graph keeps sort of snaking up vertically, like a sine graph going up the y-axis, if you have been introduced to trig yet. A relation is a set of ordered pairs. Any collection of xy coordinates that I give you is automatically going to be a relation. And then a function is a special type of relation. So think about, if you have studied any geometry at all yet, a straight-sided figure with four sides is a quadrilateral. If the opposite pair of sides happen to be parallel, well, then it's a parallelogram. If the opposite sides happen to be parallel, but the corners are right angles, like a piece of paper, then that's not just a quadrilateral, it's not just a parallelogram, it's a rectangle. And then if all four sides happen to be equal, then it's a square. So a relation, the difference between a relation and a function, all functions are relations. But for, you just saw the previous definition, a function is a special type of relation. A mapping of domain values, or you could read possibly in your textbook or hear from your teacher, independent variable, explanatory variable, the input value. Those all say the same thing, and they all, at least in terms of graphing on an x-y axis, they all mean the x. A mapping of domain values, again, independent explanatory or input value, is mapped to a range value, or mapped to a dependent value, or mapped to a response or output value. And a little bit more simply stated, without all that sort of alternative vocabulary, a domain value may be mapped to or connected to more than one range value. And to make this even simpler and write it in terms of, again, graphs, a x value may be mapped to or connected to one or more y value. Now, don't just focus on the x and the y, because vocabulary is very, very important in mathematics. You might have a test question or word problem that uses some of this language that, if you knew the language, you could do the problem. But if all you think of is in terms of x and y's, you won't understand how to work out the problem. So we have, again, this pairing of something could be a domain range, x, y, independent, dependent. Those go together. Explanatory and response values, and input and output. That's how they kind of pair up. And that is the difference between a relation and a function. If you want a more in-depth understanding, or understand what this idea of this thing called mapping is, check out the link above my head or in the description of the video for a full-length introduction to the difference between and understanding the relationship between relations and functions. Let's move on to another grouping of these 10 graphs. I got your grouping of graphs right there. How about graphs of C, E, and J? C, or excuse me, that would be J, C, E. All those graphs are a bunch of dots. Not whatever this is called, where all of these lines seem to just sort of go on, and I can't see the individual points. Those are examples of discrete graphs. A graph of isolated points where you can see all those individual points. We're going to be talking about domain and range at the end of this lesson. And if I wanted to talk about the domain and range of that's included in this graph, I would be just listing off a bunch of numbers, because there's a dot, there's a dot, and there's a dot, or a point, and there's a point, and there's a point, and so on and so on and so on. And really all of these graphs are a collection of points, but some of these graphs, the points are so close together, they're infinitely close together, you can't distinguish them. And thus these other types of graphs, it's going to be the next grouping in our lesson, are constructed of an infinite number of points. And here with the discrete graph, I guess it could go on forever and maybe still potentially involve a infinite number of points, but there's a lot of points that are left out. Actually, there's different sizes of infinity. Okay, so, and also this definition, these concepts of discrete and what's coming up, I'll give you a hint. It's a continuous graph. That vocabulary will come up again in statistics and have a lot of meaning in those application problems, those word problems. So let's move on to the second group, another grouping of graphs which are not discrete. Well, if a graph isn't discrete, it's going to have to be continuous. And a continuous graph is a single unbroken line or curve that you can draw without picking up your pencil. And if you want to know how to prove if a graph is continuous at a point using some fancy calculus stuff, that link will be above my head. Just one example of where this definition will come up again. And I said, we already, in statistics, you'll learn something called a discrete variable and a continuous variable as well. So these definitions, and this is only applied to graphing, but they come up over and over again in your math studies. And you can draw these without picking up your pencil. So I can, drag along this line. There's a sort of a sharp point there and go in another direction, but I can draw that entire, well, really it's a linear absolute value graph without picking up my pencil. I can draw this in ellipse, which, by the way, again, that ellipse, first time I've said that, would fail the vertical line test, and thus this is a relation and not a function. So I did mention it's a continuous graph, not a continuous function. And that grouping is A, B, D, F, G, H, and I. So let's move on to a different vocabulary here, vocabulary word, and a different grouping of these 10 graphs. 2 more groupings of these graphs are groupings of A, B, F, and I, and B and D. And you'll notice that graph B is showing up in both of these groups. Well, these groupings represent vertical and horizontal symmetry. This is a type of reflectional symmetry. One where one half of the graph is a mirror image of the other. So you can just draw a line right through the graph, and or if this were a big sheet of paper, right, I could fold the paper and then kind of like look through it, and the graphs are going to perfectly line up with each other. So when I look at A, and where's my compass at here? Or my, not my compass, but my protractor. I think I called this my compass earlier in the video. Anyway, if I put a vertical line there and I fold the chalkboard on itself, this line is going to exactly, if drawn correctly, line up on itself on the other side. Now B, you'll notice that B is in both of these groups. Well, I can put a vertical line here, and this will fold over and line up exactly to the left, or I could put a horizontal line and maybe fold the bottom up, and if drawn correctly, that bottom part of that graph will lie right on top of the top half of that graph. Now, just to make sure that you understand that this horizontal and vertical symmetry doesn't have to be the x and y axis, we've included the graphs of D and I. Indeed here, the horizontal line, let's go ahead and put that in here. This horizontal line, maybe drawn a little bit better than that. If I were to fold along, I probably should be a dotted line, but if I were to fold along that line, the top half of this parabola would line up exactly with the bottom half. And same thing here, if I put a vertical line through x equals -1, this left side, when folded over, would, if drawn exactly correctly, would line up right on top of the right-hand side. And that is what you're going to look for when identifying lines of symmetry. Now, I didn't include J simply because the points, well, I don't know, maybe you could argue that they're symmetry or not, but if you draw a vertical line through, that sort of line is the graph itself. There's nothing to the left or the right. There is no left and right halves that are mirror images of each other, except that there's nothing to the left of the line and nothing to the right. So let's move on to, let's see here. The next grouping that I'm going to be doing is smooth curves. So what curves up here are smooth? No. Smooth curves have no sharp bends. So in this group I'm including B, D, F, G, and I. Depending on what your teacher wants, I guess maybe you could include these curves here that are made up of a discrete number of points because there's no sharp bends, but I have a little bit of a problem including those because, well, it's not a continuous graph. But these are forming a smooth arc or a straight line. I'm only including the continuous curves of, again, B, D, F, G, and I. Simply no sharp bends, whereas A and H have two sharp bends in those. And by the way, this is an example of a piecewise function because there's three straight line segments that constitute this entire graph. We're going to be talking about piecewise functions not too far from now. And again, this is a graph of a linear absolute value function that has a sharp bend at the x value of 0. Now, this is only a definition that's based off of drawing. I can just see, is there some place that I could, hurt myself on that sharp bend? There's a much more sophisticated way of proving if a curve is smooth at a point involving calculus. That link is above my head or down in the description of this video if you want a little bit of calculus in your algebra lesson. Okay, so now we're going to move on to what an increasing and decreasing function is. Now, I want to erase all this and include just all the definitions up here at once, and then include an example where we identify intervals where a function is increasing and decreasing, but just verbally, before we get on to that, because we have all these nice graphs up here already, a function is increasing if, as you read it left to right, you notice that it's moving up to the right. And I'll give you a real definition in words in a second. So graphs that are going up to the right, and decreasing, a graph when it is decreasing is going down to the right. So this is sort of like a decreasing line and an increasing line, and you read graphs left to right like we read our English books. So this graph is both decreasing and increasing over two intervals. That's what I want to formally teach and have written definitions on the next screen, but it's decreasing from -infinity down to 0. It doesn't. and there's a sharp bend at 0, so it's decreasing as you approach 0, and then from not including 0, but just to the right of 0, and then on to infinity, it's increasing. This not being a function, it's almost like you would have to break this graph up into quadrants, so I don't really want to talk about increasing and decreasing there, because say from 0 to 3, the graph is going up to the right at the same time as it's going down to the right, because that's a relation and not a function. This graph is all the way along. Now it's a bunch of individual dots or discrete, but as you go to the right, these dots are getting higher and higher or farther above the x-axis. The y values are increasing, so that is increasing. This is going up as you read left to right. I see there is an arrow pointing down there, but as you read left to right, this graph is going up, so it's increasing until you get to 0, and then it starts to decrease. We have talked about this vocabulary of increasing, decreasing, and constant in a previous algebra lesson. Here we have a portion of this graph, this piecewise function, that is constant, and then it rises to the right, so there is an interval in which the graph is increasing, and then it's constant again. This graph is decreasing through basically forever, throughout the entire domain. It's falling to the right. That's called monotonic decreasing, if you want to be specific. So let's get these out of the way, write these formal definitions of increasing and decreasing on the board, and get a graph up here where we're going to identify and put it in writing what I've just done here verbally, identifying intervals where a function is increasing or decreasing. Increasing function. A function is increasing when the range values, the y values, increase as the domain values, the x values, increase. Again, you want to read these graphs left to right, and as the x values get bigger, you're going to the right. If a function increases throughout its entire domain, all of the x values that are included in the graph, then it is said to be an increasing function or monotonic increasing. I had some of those examples in the previous board. One maybe is like a graph that kind of curves up and keeps going up and up and up and up more as you go to the right. Those are generally going to be exponential growth functions. A decreasing function is decreasing when the range values, the y values, decrease, get smaller as the domain values increase. If a function decreases throughout its entire domain, in other words, as you look at the entire graph, and you include all of the x values, if it is decreasing throughout that entire domain, it is a decreasing function, or again, said to be monotonic decreasing if your textbook uses that phrase. Now, when you draw functions like parabolas or this little curvy thing I've done going up to the right, or this line going down to the right, we have to put arrows on both sides if that graph continues in both directions forever. But again, we don't read graphs from right to left as we're identifying intervals where the function's increasing or decreasing. Now, these definitions are for an increasing function and a decreasing function, and part of that definition is it's increasing or decreasing over the entire domain. My example here is a graph. Actually, it would pass the function test. It is a function. Every vertical line you draw is going to only have one y value. But it is not an increasing or decreasing function. It's simply a function, but there are intervals along this domain where the graph is rising to the right, increasing, horizontal, constant, and decreasing a little bit. And it's tracking a person's age from the time they're born through the time they're 65 and beyond. And we understand how we, as humans are, right? We grow, we stay the same height, and then eventually as we grow older, the cartilages between our bones and everything start, especially in our back, start to wear, and we actually shrink a little bit. So this graph is increasing from 0 to, well, let's say 18. Or you could say that it's increasing from the interval of x is greater than 0 and less than 18. There's another way of writing that using interval notation, and you would see that that interval notation maybe if you were like in my pre-calculus class, but I wouldn't use it for algebra. At least it's not in the algebra textbook I'm teaching from. Then we have a portion of this graph where the x's are changing but the y's are staying the same. Basically, it's a horizontal portion of the graph, and that's constant from x is greater than 18 and let's just say it's less than 45. And then from there, I'm exaggerating to make sure that you can see that I've drawn a portion of this graph where it is falling to the right, and therefore it's going to be decreasing from the x values of 45 to, you know, however long it is a reasonable lifespan for a person. But I don't want to say, you know, it goes to 100 because people have lived beyond 100. And maybe eventually people live, you know, 110, 120, 130 years. I don't know. So I'm going to go ahead and say that that it's going to decrease from 45 on to infinity, even though that's not really a realistic domain for an idea of tracking somebody's age. It also wouldn't make any sense to have any negative ages because you're going to be negative 10 years old. Okay, so anyway. And this is actually reinforcing some vocabulary that I've done in a previous lesson as well in our algebra class. So, also before we move on to identifying domain and range, defining it and identifying it in a graph, please note that I'm talking about the intervals along the x-axis. A lot of students would want to say that this graph increases from 1 to 6. Yes, the y value goes from 1 foot to 6 foot, but when we identify intervals where a graph is increasing or decreasing, we're talking about the interval along the x values, because, you know, and you can see that as part of the definition, is a function is increasing when the range, the y values, are increasing as the domain values. It's about those intervals along the x-axis where you want to identify if the function's going up to the right, horizontal, or down to the right. Let's move on to domain and range. Bam! Bam! So you want to identify what domain and range is. When you look at the graph of an equation, well, then you're going to have to know the definitions and the set of all possible input values, usually the x variable, which produce a valid output from a given equation. Or you can say it is the set of all first elements in ordered pairs. And ordered pairs are ordered pairs are a grouping of two numbers, which is the domain and range, the left-right movement and the up and down movement. Or if you're talking about your graph being on the Cartesian plane, that would be the movement in terms of the x-axis, and then the y value, or the movement along the y-axis. The x values included in the graph on the Cartesian plane. Okay, so yeah, usually it's x comma y, unless you're looking at some kind of graph that is, you know, displaying a real-life scenario where there's some real context to what the horizontal and vertical axis are, such as maybe, again, the age being along the horizontal axis or the x-axis, and your height being along the y-axis. And I'm saying again because I'm going to make this lesson we're watching right now is actually an excerpt of a full-length lesson. The range is the set of all output values from an equation. And it's very difficult to determine what the range is from an equation unless you're very knowledgeable. You have very strong knowledge of what all sort of the parent functions, if you will, like if you know what a standard line looks like, a standard parabola, a standard absolute value linear function, maybe even square root functions and such. If you understand and you know what those parent functions look like, and you're very knowledgeable of, say, translations, and in this lesson is for an algebra class, we haven't even gotten to that yet, I would strongly suggest you create a graph from that equation first before you're trying to determine what the range is. But the set of all output values from an equation, the set of all second elements, usually the y values in ordered pairs. Again, if you're talking about a domain range type organization, an ordered set, that's usually an x and a y value. So let's move on to our three examples. We have here an ellipse, and the domain, it seems like, again, remembering that this graph is made up of an infinite number of points, each of those individual points having, well, I guess maybe there's a couple of points with the same x value, but really kind of each of those points sort of having their own value of x, their own coordinate, right? Because that point, a coordinate describes how you get from the origin to that point. There's some kind of left-right movement, a negative x or a positive x, and some up and down movement, a negative y or positive y. So what values of x are included in all of these points? Well, the domain, looking at that horizontal movement, is going to be x. The smallest value of x that's included looks like it goes as far to the left as -3, and then as far to the right as +3. And this is a smooth, and actually being smooth isn't really important. This is a continuous graph, so every single -3, -2.9, -2.9, -2.7, -2.6, 9.5, 3.821, like any x that you can say that is between -3 and +3, including those values, would be part of the domain. In the range, it kind of looks like an N there. My range then would be all of the output values if I were looking at an equation. But graphically, we are looking at, again, this is the x-axis and the y-axis. The range are all the y values that are included in that graph. Now, again, that graph is continuous, so it seems like it goes as far down as -2 and as far up as +2, and every single y value is included between that -2 and +2. So the range is going to be y is going to be greater than or equal to -2 and less than or equal to +2. And I'm writing these in inequality notation. In a pre-calculus book, you might see this in interval notation. So I'm not liking the fact that color doesn't match now. In number 2, actually, my air conditioner came on. I know that kind of bothers the video sometimes a little bit, so let me shut that off and come right back. Okay, now that's better. Our second graph is a collection of 5 points, and if I want to list the domain here, then I really just need to write a list of values for x. Because this is a discrete graph, I can see, chalk down, that there's only 5 points. So we have an x value of -1, a x value of 0, 1, 2, and 3. And my y values are, now I don't need to repeat the same y value over and over and over again. I can just see that this point has a y value of -2. And it is a good practice to write these from low to high. Then we have a y value of, from the origin, we have to go down 1, so the y value is -1. And finally, we have a y value of +1. Okay, and that is how you list domain and range for a discrete graph. Excuse me, you have to just list all the individual x and y values. Now, if I were to come back here and change this example to one that kind of seems to go on forever and is continuous and not focus on those 5 discrete points, well, now my domain is going to be, and I really am intending on writing these in different colors. Now my domain, well, this graph goes, it's going up, but it's spreading to the left and spreading to the right forever. So the domain is all real numbers. And so you can say that x is either all reals. You might have a textbook that kind of uses a double R for all reals, or you could say that x is less than, or excuse me, greater than -infinity and less than +infinity, because again, it goes on forever. And you can't say equal to infinity because that's sort of like an infinite concept. It goes on forever and ever and ever and ever and ever. And the range, well, the smallest, again, all these points are in here now. There's an infinite number of points, and the smallest y value, or the point that is the farthest down on this graph, and then from here the graph kind of just goes up forever. So the smallest y value is -2, so the range is going to be y is greater than or equal to -2 and less than infinity, because that parabola is opening up forever, so the y values are just going to keep getting bigger and bigger and bigger and bigger and bigger. But the smallest y value included is a concrete value of -2. Now for our bottom graph here, we have a graph that seems to go left and right forever. It seems like there's no breaks in this graph except at 2. So our domain is x cannot be equal to -2. Or you may write that x is greater than -infinity and less than 2, and x is greater than 2 and less than positive infinity, if your teacher wants you to write it that way. And now the range values get down with it. The range values are all the y values that are included in the graph. Well, the graph is nowhere do you see a purple line below this horizontal asymptote, this horizontal line that is at y is equal to 1. So these y values are going to get smaller and smaller and smaller. Maybe here it's at 2, maybe it's at 1.5, 1.1, 1.0000001. Now, I'm on the left side, right, where the x's are negative, but y is still positive. And it's going to get closer and closer to that y value of 1, but never really become 1. So we're going to say that the range is y is less than 1, or excuse me, not less than 1, greater than 1, unless, now this goes up for ever, right? So y is never going to stop growing. So y is less than infinity. Okay. In an upcoming algebra lesson, we're going to be talking about identifying min and maxes. This parabola has a minimum y value of -2, but because it goes up forever and never stops going up, we could not say that there's a maximum value, unless you want to say the maximum value is infinity. But when we talk about identifying maxes and mins in a graph, we're looking for a concrete, like a real answer, if you will. So this graph has a min of -2 and a max of +2. This function, this parabola, has a min of -2 but has no maximum. And this graph is approaching 1, but it's becoming infinitely and infinitely and infinitely and infinitely closer to 1, but it's coming down from above it. But because there's no concrete number that the graph will actually ever become, this graph also does not have a minimum, or, because it's going up forever, a maximum. And if, again, you want to talk about finding domain of an equation as opposed to just finding domain from a graph, I'll have a link to that video lesson above my head, or again, down in the description if you aren't using Flash because you have, I don't know, an iPad or something like that. So, I'm Mr. True. Go do your homework.